Hello, everybody. Today we'll be discussing automatic pathing and traversal algorithms for unmanned aerial vehicles using LiDAR technologies. I've had the opportunity over the past year to work on multiple projects in which I acted as the navigation architect for a drone system, and I have been able to personally observe the efficiency changes associated with the different implementation options I will be discussing. UAV autonomous navigation is a growing dynamic field, which is greatly impacted by any improvements in efficiency. The ability of a UAV to perform adequately scales with the hardware, software, and algorithms available to the field. This study will focus on the algorithms as they apply to navigation. The aspects of autonomous navigation that must be optimized to the highest degree include the effectiveness of avoiding obstacles and efficiency of path generation without inputs from an external source. Depending on the use case for the UAV in question, the weight of importance associated with these and other values may shift. There is no widely accepted solution for the optimization of this process. Each company uses a variety of hardware, software, and algorithms to achieve their purpose. Each has varying results, but no approach has yet been demonstrated to be definitively better than any other. For the purposes of this study, the effectiveness of the solution is evaluated based on the time the drone takes to reach a given target, counting any collision as a fatal error. An optimal algorithm will also minimize misdetection and false alarm events. A misdetection event occurs when the UAV observes an obstacle where there is none, or fails to observe the obstacle when it exists. A false alarm event is the case that the drone detects a critical case when it should not. The image attached depicts a simplified example of the problem. The drone must navigate within a three-dimensional space to reach the selected target while avoiding a variety of obstacles. The first step in the process of autonomous navigation includes machine vision. Using a combination of vision-based and inertial sensors, the system is able to gather enough information about the environment to navigate through it. A drone must have access to a vision-based technology that is able to rapidly generate sizable inputs based on the largest possible proportion of the environment. It must also be able to efficiently transform these inputs into a usable set of values, which represent the coordinates of the nearest obstacle in every direction in the 3D plane relative to the drone. It is important to consider how efficient the hardware component for machine vision is, as a function of the time it takes to return updated values and the area that the technology is able to see in. For this study, I have selected the VLP16 LiDAR as the vision-based hardware for data collection. A LiDAR collects input in the form of laser reflection. Distance and dimensions of objects are able to be measured based on the time it takes for the light waves to reflect off of obstacles and return to the sensor. In addition to providing the user with data points that contain information about the position of obstacles, it may provide other useful data, which includes the material and density of the identified objects. This information may be useful for determining how dangerous a given collision may be. LiDARs do not detect fires because they do not significantly reflect or refract the light of the laser. For projects in which the inability to detect fire becomes an issue, an infrared sensor is used in coordination with the LiDAR. The LiDAR provides data more accurately than other leading vision-based hardwares. This comes at the cost of increased load and power consumption for the UAV. The image shown here depicts the form in which data is made available. We're able to view a grid of points in which the intensity varies based on the objects being reflected. In a centralized approach, the data is gathered and computed remotely before it is communicated to the drone. This enables the use of more powerful computation, but increases the overhead communication time and limits the ability of the UAV to deal with real-time problems. Due to these issues, the accepted model functions locally to the vehicle, using reinforcement learning to allow it to have sufficient intelligence to focus to function without the need for a central computer. The decentralized approach requires the UAV to have a powerful enough onboard computer to perform all calculations and have the ability to handle the additional load associated with the vision and calculation hardware. A majority of active solutions consider obstacle avoidance and pathing to be one and the same. Logically, if a drone is able to navigate around obstacles from its current point to its target point, it has succeeded. In this case, what use would an additional algorithm for obstacle avoidance serve? The answer is simply that uh, completing the mission is not sufficient to consider a success. There are many limited resources to consider, such as time, memory, computation, and durability. For each clock cycle in which a simple obstacle avoidance algorithm is able to be run at the expense of a full run of the pathing algorithm, there are savings in terms of both memory and consumption without compromising time or durability. In each iteration of the pathing algorithm, data must be obtained, compared, grouped based on clustering, and drawn into groups of points which represent an obstacle. At this point, the algorithm may select the path that best brings it towards the target without collisions. In each iteration of the obstacle avoidance algorithm, data must be obtained and an efficient check is performed to see whether any points intersect the drone's current trajectory. It is clear that the obstacle avoidance algorithm is much more efficient than the pathing algorithm, though it cannot accomplish the same results. Suppose that of the obstacle avoidance algorithm takes only 15% of the time of the pathing algorithm. For the sake of simplicity, suppose that there exists a UAV system that runs pathing algorithm 5 times per second. Let this process compose m computational time. A large amount of computation is used despite the fact that the path of the drone cannot be expected to change many times within such a short interval. If an obstacle avoidance algorithm rather than a pathing algorithm is invoked in place of 3 or 4 of these iterations, the total computation spent is reduced from m to 0.49 m or 0.32 m respectively. With the computational power saved by substituting some uh, instances of the pathing algorithm with a general obstacle avoidance algorithm, the area can be surveyed 5.2 or 10.6 times more per second, leading to a much greater ability to avoid moving objects or a lower amount of strain applied to the onboard computer. The pathing algorithm must, of course, be invoked every time a change in path is necessary, often due to either avoiding an obstacle, viewing a significant change in data, or reaching the end of the defined path. Finding the balance between running each of these algorithms will improve the overall performance of the autonomous navigation tasks. These algorithms commonly consider drones to have a safety bubble of a given size, though it can vary across the algorithms. We will refer to the minimum distance from an object a path can be planned as the warning margin, and the lower boundary on the distance of an obstacle before avoiding it will be called the evasion margin. Given a set of points translated from the input with noise removed if possible, there must be an algorithm to process the points with the goal of analyzing their proximity and available space. Based on this data, paths are defined and a decision is made which path to travel down. When the optimal path is determined, a waypoint is sent to the drone. A waypoint is a position relative to the world that the UAV is expected to travel to. If multiple waypoints exist, they are labeled sequentially in the order they will be visited. Once the drone has visited a waypoint or otherwise overridden it, it is removed. The pathing algorithm must be invoked whether a change in trajectory is necessary or when the drone has reached its final waypoint. It is often rerun before one of these conditions makes it necessary. This function uses an input set of points that have been translated from the LiDAR and had noise reduction performed to reduce the likelihood of misdetection. A path is scored more highly if it strays less from the direct path to the target, which is only sometimes a viable path. Penalties for data points can vary by the goal, but may include retracing steps, moving into a confined space, or collisions. Collisions may be penalized either as a major penalty for any collision or as a variable penalty based on the depth of the collision. After the path has been selected, there will be frequent communications between an obstacle avoidance algorithm and the flight controller, taking in new perception data each cycle. The process ensures that environmental conditions along the path have not changed to the extent that it becomes unusable. If this is found to be the case, the path will be canceled and a new set will be calculated. A reinforcement learning approach may be applied such that the pathing algorithm assesses the results of its choice by interacting with the environment in its next state. Based on the level of improvement, if any, from the previous state to the current state, the UAV may find that it benefits from altering the weight of each decision criteria to optimize the path evaluation process based on the parameters of the current environment it is in. For example, if the UAV is traversing an environment designed like a typical maze, the optimal weights would differ in favor of detecting and avoiding dead ends, and penalties for moving into confined spaces of a reasonable size would be reduced. This is reasonable because of the environmental parameters of mazes. They often maintain a relatively constant size along each path, but have many dead ends which the drone may learn to avoid. The Markov decision process is a special case of reinforcement learning. It deals with data which is defined as a tuple of state space, action space, reward space, and the probability of a timely state transition. The state space is defined by the UAV position, the presence or absence of a target, and the states of each cell. The optimal policy is chosen by actions that maximize a state action value function. The state estimator estimates the best state to transition to based on the net previous probability distribution and the current observations of the drone. The policy estimator determines the best action to be taken. After reaching a new state, it reevaluates its decision to see if a different policy with different weights for its scoring criterion would have been more optimal. Once the trajectory has been confirmed, the UAV is able to continue safely along its path. It will move along the selected trajectory through the waypoints, but it is still possible for moving obstacles and changing environmental conditions to affect the safety of the selected path. As the drone travels, it can account for these changes by continuously collecting data and checking for immediate collisions of the drone along the current path. If any obstacle is detected in this way, the UAV must affect its movement such that the collision will no longer occur. If it moves in this way, the navigation process must repeat, such that the path can be recalculated. Additionally, the path will be recalculated either upon reaching the end of the planned trajectory or after a set amount of time. This ensures that the UAV does not move blindly, and it alters its path to account for environmental changes even outside the realm of the selected path. One approach being utilized to calculate paths is separating the process into discrete actions, which involves segmenting the scene into a grid system. Rather than using clustering to calculate where an object exists, one can simply try to avoid any grid space containing any obstacle data point. While this may simplify the process, there are also problems associated with it, such as increasing the effective size of obstacles and enforcing space limitations on the algorithm based on the maximum grid size. A continuous action space does not use the grid system, instead requiring the algorithm to calculate the difference between points to ensure sufficient space for the UAV to travel around and between obstacles as needed. More data points will correlate to more proximity calculations between these points. This eliminates problems associated with discrete action spaces, meaning the drone can potentially move closer to obstacles or see further, but it comes at the cost of a worst case efficiency. In the example image, some of the obstacles are found along the path to the destination in a discrete action space. The width of each square within the action space is identical and corresponds to the warning margin associated with this algorithm. The obstacles in the scene are likely not perfectly rectangular with that specific width, but they are detected as such by the pathing algorithm in a discrete action space. It is possible that these obstacles take up only a small fraction of the space assigned to them. Therefore, it is likely that a pathing algorithm in a continuous action space would guide the drone along a more optimal path, possibly decreasing travel time. The greater worst case efficiency of the pathing algorithm in a continuous action space dictates that the computational efficiency of such an algorithm may be greater than its discrete equivalent. After the waypoints have been communicated to the drone, trajectory planning may be utilized to determine a way to travel between the waypoints with minimal decrease in speed. This calculation can optimize travel speed given that multiple waypoints are calculated, or the next waypoint constitutes a significant directional change. This action may create increased difficulties as determining the optimal trajectory given the speed of the drone and location of waypoints often results in a convex path. In that case, the newly calculated path must be checked for collisions. Hard constraint trajectory planning is the process of sequentially adding waypoints and determining the best trajectory from one to the next. Alternatively, gradient-based trajectory planning may involve calculation of multiple waypoints at the same time by plotting different trajectory types in parallel and selecting the best. These trajectory types may include an optimistic trajectory, which states the shortest travel time, assuming no obstacles are along this path, or the risk perception trajectory, which takes obstacles into account, or a trajectory that factors in the drone's current yaw angle. In either a discrete or continuous action plane, it is possible to interpret environmental data as a map of obstacles. The map may only include the drone's current and previous positions. It can be expanded by overlaying the currently detected terrain onto the set of previously detected terrains, shifted for distance of drone travel. Mapping is not the main goal of obstacle avoidance, and only a small amount of time may be allocated for it. The aim of the mapping algorithm is to minimize the uncertainty of the mapped environment within a fixed maximum amount of time. The map created will not be perfect, but will be useful for continued navigation within the current environment. It allows the UAV to observe environmental features that may have moved or otherwise changed, and it also allows it to optimize for the path not taken. My master's project is one example of an application of UAV autonomous navigation. The goal is to automate a set of drones which are able to detect and suppress fires remotely. My goal in this project is the team lead for navigation and avoidance development. We use LiDAR as the vision-based hardware, mounted in a way that it is able to see the optimal amount of the terrain, both in the plane of the drone and in the vertical plane. The data collection performed on the LiDAR data involves both spherical and cubic coordinates of obstacles relative to the drone. DroneKit is used as the flight controller, which provides the drone's inertial measurements and fulfills requests to alter the drone's trajectory. A hybrid avoidance system is used, which is described in detail on the following slide. Limited trajectory planning is applied as only one waypoint is to be given at a single time, and the most direct path from the drone to the next given waypoint will always be optimal. More information about this project and its methodologies can be found in the article Collaboration between Multiple UAVs for Fire Detection and Suppression, to be published in the 2021 International Conference on Unmanned Aircraft Systems. The pathing algorithm for this project, though complete, is in a state of constant development, as there are many potential upgrades for the algorithm before it is able to compete with leading algorithms in the industry. The algorithm operates in a continuous action space and is decentralized. The process, as shown in the first image, takes place across a variety of steps. The data is input from the LiDAR, then clustering is performed to determine which points belong to the same obstacles. It is then checked to see whether the most direct path to the destination is blocked by one of those obstacles. If the target is not blocked, the drone simply plots a direct path towards the destination. Assuming that the path is blocked, however, the algorithm will plot safety bubbles around the edges of each of the obstacles. The line tangent to the safety bubble is considered the most efficient travel path for the drone to navigate around that obstacle and towards the target. So these tangent lines are considered to be the set of possible paths. The path that is determined to score the highest is used to determine the next waypoint at that tangent of the point. The obstacle avoidance algorithm is a shorter runtime algorithm to determine if a data point exists along the current path. All points that could not cause a collision are eliminated. This is done by creating a subset of all points within the x, y, and z components of the drone's velocity. A calculation of this variety allows for the evasion zone of the UAV to vary based on how fast the drone is moving. From the subset of data points, if any, the angles of these points are judged by comparison to the angles of the velocity. If any matches or near matches occur, the algorithm will report a collision and avoid the obstacle. and the pathing algorithm will be repeated to find a new valid path towards the target. The obstacle avoidance algorithm are applied within an embedded systems loop, which runs in a thread of its own and continuously invokes the appropriate algorithm at the correct time and repeats it thereafter after a set time interval unless it is directed otherwise. Thank you for your time. Please let me know if there are any questions.